Okay, good afternoon, everyone. Welcome back to this lecture today. We will be covering equivalent circuit of three-phase induction motors. So just as a recap, we talked of three-phase induction motors last time, and we mentioned that the key principle of operation was rotating magnetic field. So in order for us to now move beyond the physics of the machine, we will now be looking at, from an electrical point of view, how do we create a circuit for the machine? Right? How do we arrive at a circuit that can represent the operation of the machine? As we look at a three-phase induction motor, the way we had said, we mentioned that if you look at a cross-section of the motor, it has its stator. And inside the stator, of course, you have windings that go, they are distributed all around the inside of the stator. And those represent three phases that you would generally be able to, cover the entire inside surface. And those three phases, as soon as they are connected to power, as soon as a three-phase supply is connected to the machine, you get a rotating magnetic field that is experienced by the rotor. If that is your rotor with its rotating, or with its bars connected in there, you would have a magnetic field that rotates in that direction, and also your rotor itself would rotate at a speed indicated by N, and the rotating magnetic field would rotate at a synchronous speed Ns, right? And also we said that the relationship between the two is given by slip. So slip is equal to Ns minus N over Ns, sometimes expressed as a percentage. So it's a fraction, or it can be a percentage. Now, when we are looking at the three-phase induction motor, it is often analogous, or it is useful to think of it as being analogous to a three-phase transformer. So there are a lot of similarities between a three-phase transformer and a three-phase induction motor. Yeah. So there are a couple of similarities. A three-phase transformer has a primary winding and a secondary winding, whereas the three-phase induction motor has the stator and a rotor. Okay, these are analogous to each other. The key difference, of course, being the primary winding and the stator are fixed, both are stationary. But in the three-phase transformer, the secondary is stationary, but the three-phase induction motor has a rotor which is free to move. Yeah, it is free to rotate following the rotating magnetic field that is induced. So in that sense, yeah, we could be able to say that we could represent both the three-phase induction motor and the three-phase transformer using this set of windings that we have, whereby you have your primary on this side and your secondary on the other side. And in the case of the three-phase induction motor, you have your stator and your rotor. Okay, those are the analogous points to that. Okay. Similar to the transformer, you also have in your three-phase induction motor, you will have a turns ratio for both of them. In the transformer, it is denoted by A. In the three-phase induction motor, we have what you call an effective turns ratio. All right, an effective turns ratio. Okay, denoted by A effective, which is the ratio between the windings of the stator and the rotor bars of the rotor. All right. So far, so similar. Okay. Now, similarly, in the same way that you have three-phase windings in a transformer and in an induction motor, you are subjected to the same kinds of electrical components or electrical parameters that you would have in both the transformer and the induction motor. So some of the phenomena that you would encounter, first of all, would be number one, you can say you can encounter copper losses. And copper losses are in the form of resistances. Okay? Because these windings that you have are both windings that are, you know, they are made of copper. They are real world things that have resistances, so you have to account for that. So in drawing our three-phase induction motor or our three-phase transformer, you would have a resistance at the primary side, and you would also have a resistance at the secondary side. And this is the same for both the transformer and the induction motor, right? So this is representing copper losses and copper losses on both of the windings. So you have copper losses for stator and copper losses for rotor. Okay. So that's number one, copper losses. Number two, these are machines that induce electrical or rather magnetic fields. So magnetic fields, the fields that are set up around the windings, will encounter what you call leakage reactants. Leakage reactants. And what leakage reactants is, as you set up a magnetic field around the windings, some of that magnetic field does not link with the opposite set of windings. So the magnetic field that is set up in the stator does not all link with the magnetic field, or rather with the windings or the rotor bars that you find in the rotor, and vice versa. So within the rotor, we mentioned that as you set up, in order for you to have torque, you would have a counterpart magnetic field that is set up inside the rotor due to the current that flows inside the rotor. Let me just show that. We had that before, somewhere here, under rotating magnetic field. We had shown that when we are doing the torque, here it is. So we had shown that you have the rotor bars themselves setting up currents within themselves. Okay, so these are the ones we are talking about. So they have magnetic fields being induced around each other. So let's just go back to what we are writing here. So in this case, we then have a leakage reactance, which is represented on both the stator and the rotor. So you have it here on the stator, and also you have it here on the rotor. Okay, so those are both there. So these are leakage reactances. So leakage reactance, leakage reactance in the stator, and leakage reactance in the rotor. Right? Okay, so far we have two phenomena. In addition to that, you have, due to the currents that are flowing within the stator, there is an element of the currents that will be taken up as losses due to eddy current. Okay, so you have eddy current losses. These are currents that are set up within the windings, and they are generally represented as reactances. Losses are represented as reactances due to the eddy currents that are set up within your machine. So let me shift this. Generally, the convention is to represent them at this point. So you would generally represent them as that. You have that. Okay. Eddy current losses, which are represented there. And a counterpart to the eddy current losses are hysteresis, and core losses, right? And these are resistances. Okay, so that is represented here. Okay, yeah. So these are hysteresis losses. Okay, let me label them a bit better. So in order for us to make a bit more sense of this diagram, let me try and label them a bit better. So we have, let's give them representations. So generally, the way they are represented, your copper losses are denoted by R1 and RR. So R1 is on the stator side. I'll just write them in here. So let me label them with their labels. So you have R1, which represents copper losses for the stator, and RR, which represent rotor copper losses. Then corresponding to that, you have X1, which represents the stator leakage reactance, and XR, which represents leakage reactance within the rotor, right? These ones here are represented by XM and RC. RC because these are core losses. XM because these are magnetizing current losses, right? So XM. And also bear in mind, anything that is represented as a reactance is always perpendicular or orthogonal to the resistance, right? Those are complex quantities. Those are imaginary quantities, okay? So what we've now ended up with is a pretty good representation of the three-phase induction motor circuit. And because we are looking at it electrically, let's add various other parameters that we have. So of course, on this end, you would have the voltage supply, all right? So that means that at this end, you have a phase voltage being supplied. So this is a per phase equivalent of the three-phase induction motor, which means that every set of windings on each phase has a circuit that looks like this, all right, corresponding to both the stator and the rotor, okay? We have supply voltage being put in at that point, supply voltage. There is a current that will flow in through the supply voltage. We denote it by I1. And the supply voltage will be the frequency at supply voltage. Let's call it SE. SE representing the frequency of the voltage at the stator. Okay. And then at this other end, you would also have a current that passes through here, IM, which is your magnetizing current. And that magnetizing current is the one that we talked of, that is going through, that is being lost in parallel to the, can we call it the ideal transformer ratio that is here. The magnetizing current leads to leakage, not leakage, but rather the eddy current losses and the hysteresis losses and core losses. So resistances due to the core of the machine itself, not due to the windings. That is represented by this arm that we have here. So you have an arm here that represents the magnetization bit. And finally, in the stator side, you have a current here. Let's get rid of these. So you have a current at this arm, which is given by I2. So that's why you have I1 and I2 representing the two currents that are there within the stator. I1 is directly what is seen from the supply end, but I2 is what actually reaches which is available to be transformed or to cross over from the stator to the rotor. This current is the one that will be seen from the rotor side. And a corresponding current will be able to flow. Now, remember last time we said that the rotor bars are shorted out to each other. So actually, there is no additional load connected to the rotor. It is a closed circuit with the supply being given by that point, which is given by E. Just trying to check what is its denotation. It is E2. And at this side, we have E1. The drawing is a bit squeezed, but the voltage that is seen from the rotor side as a supply for the stator is denoted by E1 and E2. So the rotor circuit is this one here, a supply E2, the stator, the rotor copper losses, let's call them RCL, rotor copper losses, and leakage reactants within the rotor, denoted by RR and JXR. Okay. And similarly, we have a frequency of the rotor due to the voltage that is supplying it. Now, remember, the reason why you have a different frequency at the rotor is, remember, we have this slip, right? So the difference between the synchronous speed and the actual mechanical rotation speed is this slip. So the rotation speed is just slightly less than the synchronous speed, and that is what gives you a different frequency, right? And in fact, the frequency, because the frequency of the stator is the frequency of the supply voltage. However, remember that the frequency that is induced within these bars, which was given by, which we showed here, yeah? So it's not here, sorry. The frequency was here, yeah? And we saw that for you to have this current being induced within the rotor, you must have the rotating magnetic field crossing or cutting across the rotor conductors. Remember our Lenz's law, what we said, the Lenz's law. So it is the Lenz's law that is responsible for this voltage that we are seeing on this other side, okay? So that means that in this particular case, our frequency of rotor current, which is denoted here by IR, our frequency of rotor current is much less than the frequency of the supply voltage or the supply current. And in fact, FRE is related to FSE through the slip. It is in that ratio because the ratio is the number of times that the frequency, or rather the number of times that each rotor bar relative to the rotational magnetic field would be cut across. So like, for example, if the rotor was stationary, yeah, like when you're starting the machine, if the rotor is stationary and the rotating magnetic field has just been switched on, it would mean that your slip would be given by S equals NS minus 0 because your speed is 0, right? In the stationary case, or when you're starting the motor. And that means that your slip would be 100% or 1, okay? So in that case, your starting slip would be 1, and that means that the frequency of the rotor and the frequency of the stator are the same. However, at normal rotating speed, normal operation, Slip is approximately equal to between 3 or 6%. So that means that the frequency of the rotor here would be much, much lower than the frequency of the supply or the frequency at the stator. So if frequency at stator is 50 hertz, you would have 6% of that. That would be, say, 3 hertz, for example. So your FE is much, much slower. Okay. So here what we have done is we have essentially created the equivalent circuit of the induction motor based on what we already saw as an analogy of the three-phase transformer. So let's look a bit more at it. Now, let me show a kind of pre-drawn one. So this is a bit neater than my hand-drawn diagram, but it has all the components that we are talking about, just in a clearer fashion. So starting from this side, you have your stator, and the stator has an air gap between it and the rotor. Okay, so this side is stator, this side is rotor, right? And as we look at those, we will notice that our ideal transformer, where we have the induced current crossing over from the stator to the rotor, is represented here by transformer windings, which have an ideal characteristic, that is, they have no resistance, they have no inductance, and there is an effective turns ratio denoted by A. So that is the ratio between the windings. We said that the stator has very many thin windings and the rotor has a few thick bars as its windings, right? So that ratio between the many thin windings and the few thick windings is represented by that turns ratio or effective turns ratio. And we have all the currents being represented. So you have your I1, which is what is seen from the supply side. The supply is connected there. You have your I2, which is the current that is seen as the last current before it is makes the jump across the air gap. Let's call that the air gap. Yeah, when the current or the magnetic field jumps across and induces a current in the rotor, that is the current and the voltage E1 that is seen by the rotor as its supply. So current I2 and voltage E1 are transformed through the windings into voltage ER and current IR. So the supply is ER and the current is IR. Okay. Then we represented all the elements. So R1 we said was stator, copper, losses. JX1 we represented or is meant to represent leakage, reactants in the stator. JXR is meant to represent leakage, reactants in the rotor. RR is your rotor, copper, losses. RC, these were your hysteresis and core losses. Yeah, the core that, the magnetic field within the stator is set up. And then this is your magnetizing current losses or magnetizing reactants, right? So we have now managed to label all the characteristics or parameters of our induction motor. Now, the catch that we have here, the problem that we have is this ideal transformer that we have represented within our circuit. If we were to do circuit analysis, the ideal transformer here poses a problem because we have one, looking at the motor from the outside, the phenomena that we can see are the voltage of the supply, the current of the supply, and likewise the frequency at which that supply is provided. Actually, we left that out. So FSE and FRE, which is equal to SFSE. Okay. So these three are the characteristics that we can see externally, and we are able to measure the current, the voltage, and the frequency. Now, if we have our transformer in between, we will not be able to measure this current using normal, circuit analysis, or we will not be able to genuinely measure this voltage, right? We could, but it would be complicated. So we try to unify the circuit so that it is having one supply instead of having two electrically disconnected circuits that are only connected by magnetism, but they are not physically connected to each other. So we try to develop an equivalent circuit that is suitable for circuit analysis of our induction motor. So how do we do that? We do that in two steps. The first step is we try to develop further the rotor circuit, and the second step is we try to deal with the effective turns ratio. That is the transformer that we are talking about. Okay. So let's look at how that is done. Right now, so we've already said there is an effective turns ratio, AEFF. A effective is a turns ratio, and we've already mentioned that the frequency is related to the stator frequency is related to the rotor frequency. So now, how do we deal with that a bit further? So let's look at the rotor circuit itself. Okay. So we said that the voltage, which we have already mentioned here, this ER, is dependent on how much voltage is coming from this other side, which is EI. And in fact, we will have a relationship that is given by ER is equal to the slip times something which we call R0, where ER0 is our voltage when slip is 1. That is when the speed of the motor is equal to 0. That is the mechanical speed when it is stationary. Right? So the ratio ER is related to a point, a voltage that is created when the machine is at ER0, or rather when it is at stationary, the speed is 0, right? That's point number one. Point number two, let's take a look at JXR. We see what we can do with it, all right? So in this case, JXR, which is our leakage reactance on the rotor side, let's break it down a bit, and we know it is given by omega R due to the voltage times L, which is the inductance of the rotor. Okay, this is an element that we are talking of, that is the inductance of the rotor. That is the inductance of the rotor bars themselves. And this is equal to 2 pi FRE times LR. So already this is starting to look familiar because we know this is given by FRE. So at this point already we can see we may be able to relate an element on the rotor side. We can relate it to something on the stator side, right? Which is what we are aiming to do. We want to see how we can connect the electrically separated rotor circuit from, we can reconnect it to the stator. Okay, so what does this give us? So this gives us already this FRE. We can put it in terms that we have already seen here. So that will be given by 2 pi times SFSE times LR, which is the inductance of the rotor, right? Now, let's try and create some additional components that we would want to look at. Let's create a rotor resistance R0, XR0, when the rotor reactance at speed 0. So n equals 0 when the speed of the rotor is 0. And this gives us xr is equal to s xr 0 because they are related to each other in the same way as the voltage at 0 speed and also the way the frequency is related, right? All those are related to each other. And we have already said we know what ER is, okay? So we have a number of equations that we have created. We have that, we have this, and we have that one, right? So let's see how else we can relate each of them to each other. Let's look at now this circuit on its own. So simply by Ohm's law, we know that this ER is equal to the sum of the currents times the reactances, okay? So if we write it as Ohm's law, we get ER, which is the supply of the voltage at the rotor, is given by IR, which is our current here, times what? Times the total, what did we call it? The total impedance, that's the word I'm looking for. The total impedance across, which is given by RR plus JXR, right? So now we have a fourth equation that we can look at, right? So let's transform this slightly. So we have IR is equal to ER over RR plus JXR, right? So this is our, let's use this as our fourth. We bring it here and we say this is our fourth equation, okay? Now let's use Ohm's law to play around with this a bit, okay? We had already said that equation number 3, XR is equal to SXRO, and equation number 1, ER is equal to SER0. So let's substitute those equations. So substituting, right, that gives us IR equals SER0 over RR plus JSXR0, okay? These are all things that we have seen. These are characteristics that we kind of have already known about, right? And let's transform this a bit more, just slight rearrangement, divide by sleep, okay? So that will give us SERO divided by S, and that one divided by S. That will give us ER0 over RR over S plus JXR0. So this is a useful form that we can slightly change the circuit. So if we have IR given by that, you can slightly change, yeah? So you see here we have ER and XR, which are variables. We can slightly transform them into ER0 and XR0, which are constants, okay? That means that if we use the same Ohm's law to redraw the rotor circuit, remember this was our rotor circuit, this independent bit here. If we redraw it, we end up with a circuit that looks like this. So you have your supply, which is ER0, ER0. You have a current flowing through the circuit of IR, which was already there before. And then now you have a resistance RR over S. So this is R in the rotor, resistance of the rotor over slip, right? And then you have an inductance or a reactance, sorry, a reactance given by JXR0. Okay. So in this way, we have a constant there and a constant there that we can relate to the various parameters of the machine. So we have slightly changed the characteristics of the machine, and that means that we have been able to relate it to the slip that is there. So what we have said is ER is equal to SER0 and XR is equal to SXR0. Okay. So if you were to get rid of that S, yeah, which also applies to this one, you have then transformed the circuit into a circuit that has the same frequency as the stator, right? So this is rotor circuit, kind of with at the stator frequency, right? So that's one step that we have done. So we've kind of rearranged the rotor circuit so that you have matched stator frequency and rotor frequency. Okay, we are taking a step closer. So now let's look at step number 2. So step number 2, referring the rotor circuit to the stator circuit. So we try to eliminate the effective turns ratio. So we've already matched them up in terms of frequency. Now we want to match them up in terms of the effective turns ratio. Okay. Now for effective turns ratio, let's look a bit at the theory behind transformers and how we get turns ratio in the first place. Okay. So what is turns ratio? So turns ratio given by A is equal to voltage on the primary over voltage on the secondary, isn't it? Which means that the voltage on the primary is equals to the turns ratio times the voltage at the secondary, right? Similarly, the turns ratio is equal to current at secondary over current at primary. They are the opposite of each other, right? In terms of voltage, primary over secondary. In terms of current, secondary over primary. So that gives us IP is equal to over A, right? Swap the two. Okay. Now, what if we said we want to look at from the rotor side? Yeah. If we are saying, we are using the word here referring. Okay. I'm sure you've heard this word before. We want to refer the rotor circuit to the stator side. Okay, so that means that you would have a pseudo, I don't know if I can call it a pseudo voltage or a pseudo current, pseudo elements that would be referred onto the stator side, even though they come from the rotor side. So we would label this as a stator voltage with a prime. That means it is referred to the stator side from the rotor side. And similarly, you would have a special stator current that is referred from the rotor side. So the rotor current referred to stator side will be given by these primes. Okay. That means that in the eyes of the stator, okay, what we are aiming to do is, if you look at it from the stator side, remember we had our ideal transformer that looked like that, and we had at the, this is the demarcation of the two. You have it there, so that this is stator side and this is rotor side. Okay, and if we are looking from that side, if our eye is looking at it from that side, all right, because that is where our supply comes from. So from the point of view of the supply, you have your voltage and your current being looked at from this side. So we want to see, according to the stator, what effective current and voltage does it see, right? So that would mean that if we could block this out, you would end up with a circuit that looks like this. So you have some kind of black box or impedance that you are seeing from the stator side, right? So in the eyes of the stator, all you're seeing is rotor. All you're seeing is you have your current, whatever it is. We had said it was I2, or you can call it IS, and you have a voltage. We had called it E1, yeah, and that is being seen to be supplying some impedance Z, which is from the rotor side, okay? But that Z is acting through your ideal transformer. So it is transformed from the rotor side. The actual voltage at the secondary side is transformed into a referred one at the voltage side. So this Z is a referred impedance from the stator side, or from the rotor side. So it is a ZS with a prime. And it will be given by Vs prime over Is prime. Okay. So what are we trying to say here? This Zs prime from the eyes of the stator can actually be seen as a certain impedance, which we can rename as Z2. It's a certain impedance which is renamed as Z2. And what is supplying it? It is being supplied by I2 and it is being supplied by E1. Okay. Remember what we had shown here in our diagram. Remember, I2 and E1. E1 is the supply. I2 is the current that is going in. Okay. Remember those, right? So Z2, which is what we are now calling this one, Z2 will be given by E1 over I2 by Ohm's law, okay, from the point of view of the stator, right? So what does that tell us? Now that means this Z2 and E1, if we rearrange again, remember this VS1 came from here. And what is VS1? It is given by AVS. So if we pull this across so that we can work on it, bring it here, right? So our E1 is actually Vs prime, which is actually A over Vs, AVS, right? So the E1 is Vs, which is AVS, and I2, which is there, is Is prime, which is actually Is prime there, which is Is over A. Okay, still our Z2, still what we are talking about, right? Then from there, what do we have? So that means if we simplify that, Vs over Is, you will actually end up with A squared, because this A moves to the top, right? So what you end up with is you have your impedance, your perceived impedance when you're looking from the stator is Z2, which is equal to A squared Vs over Is. Now, let's translate it once again to what we had already seen, right? Going back to this, our diagram, right? So this one we had shown previously, okay? Now, E1 here, how is it related to ER, right? And I2, how is it related to IR? Remember, these are the ratios of primary to secondary and primary to secondary, okay? So let's see how that plays out, okay? Continuing on this, okay? So now, E1, which we had seen before, is related, based on those ones, by an effective turns ratio into ER0, okay? Which is what we had seen from this side, all right? Remember here, what we had brought about here, right? So if we slightly change this around, if we extend this, yeah, this was the rotor circuit. So if we bring in the other part of the circuits, remember those ones still exist. The stator side of the circuit, which is I2 and E1, yeah, and here we have effective turns ratio. So if we take this as your primary side, which is the stator, and this as your secondary side, you can relate the two of them through effective turns ratio. Okay, so E1, these two here, remember we said A, the turns ratio AF is equals to primary over secondary, which is E1 over ER0, and also AF is equal to IR, because it is secondary, over primary. Okay, those two are there. Let's copy them onto this other page so that we can work with them to continue our derivation here. So copy them onto this side. So that comes here. And similarly, for your current, you have I2 is equals to IR over AEFF. Okay, so we have related those two. Now, your Z2, which we had created down here, is given by Z2 is equal to A squared effective times the VS, which we know is this, ER0, over the secondary, which we are given by IR. Okay, sorry, IR, right? So we have now related the virtual impedance that we had seen here from the point of view of the stator. What the stator sees, we have related it to our reconfigured circuit, our reconfigured rotor circuit that we created here using Ohm's law. And it is now, they are two matching each other. Yeah, we have a relationship that includes now the turns ratio. But we also know that due to that Ohm's law that we had talked about, remember we had this equivalency that we had talked of, Ohm's law, IR is equals to E0. So let's take this across to the other side, right? Remember we had this one that we had created. So let's bring it back into play. Okay, they're all building on each other. So now we have this relationship that we had created earlier from the reconfiguring of the circuit so that it has the same frequency as the stator. Let's rearrange it so that it looks like this. So we'll have ER0 over IR will be equals to RR over S plus JXR0. So ER0 over IR is equals to RR over S plus JXR0, right? Now let's bring this back that side. So that means that our Z2 is equals to A squared effective times all of this. So let's bring all of this here, right? All of that, okay? So effective times all of that, right? Because of the relationship of ER0 over IR, okay? So what does this now mean for all of us? So you have a Z2, which is equals to, if we split it out, A squared EFF times RR over S plus J A squared EFF times XR0, okay? Matching up, right? So that means that if we could take this element and this element, we would be able then to match it up with these two. So now what we do is, because we know the effective turns ratio, we can now call this a new element called R2, and we can now call this a new element called X2, such that you would then have your Z2, which we had created here as a representation, ZS, which we called Z2. You can now have a single impedance that you would look at from the point of view of the stator being supplied with I2 and E1, and you have your ZS, and your ZS, which is equals to Z2, would be represented by these two elements, a resistance and an impedance, which will be able to represent the two. So now we combine all of them together. So instead of having your virtual or your perfect transformer with your I2 and your E1, you are able to remove this, and it then becomes I2 still being supplied by E1 into a Z2. Okay, and what is this Z2? Z2 is equals to R2 over S, don't forget your S, over S plus JX2. Okay, so this in turn becomes converted into a resistance, an impedance, which are all E1 with a current of I2 flowing through, R2 over S, JX2. So our rotor circuit has converted from this one here. Do we have it in this page? Don't have it in this page. So our rotor circuit, which was this one here, our rotor circuit has converted from this self-contained circuit into, we now have a circuit that represents the stator, but crucially, it has 2 points where you can connect it to the stator. So bringing it all back together, okay, what you end up with, you had your stator with its impedances like that, and its magnetizing arm like that, with your supply phase voltage and input current I1. You had an IM, magnetizing current, and you had an I2 and some voltage E1 that was at this point. So these 2 points, you can then now connect all of that down here. So we've now brought about our rotor circuit and our stator circuit together, and you then have a single supply point with a single current and a single voltage, and all of it at a single frequency. So you've eliminated rotor frequency, you've eliminated your turns ratio, and you have a single unified equivalent circuit for the 3-phase induction motor that looks like this. Right? So this is now our final equivalent circuit for the 3-phase induction motor.